So we're talking about putting a space station in geosynchronous orbit and having an elevator going up to it. Well, the challenge has become, well, first you have to have a 30,000 mile long wire. That's really strong. And actually you have to have, if it's going to be a loop, you got to have a 60,000 mile long wire. And you have to have this strong enough so it can handle pulling elevators in and out. And you have to have safety features and all kinds of challenges that you would have to deal with. But it becomes an engineering issue, not a physics issue, meaning the physics says this will work. It's just the engineering part that says, okay, how do we make that work? And it'd be a challenge because, I mean, this is 30,000 miles. That's more than the radius, the circumference of the Earth. So even if your elevator was going really fast, like hundreds of miles an hour, it's still going to take you many, many hours to get up here. I mean, even if you're going 1,000 miles an hour, it'd take 30 hours to get there. So you have to have really fast elevators. And so the elevators have to be like airplanes, essentially. They have to be able to withstand these super fast speeds coming and going, otherwise you'd never get there. So there's a lot of challenges with it, but in theory, it could work. All right. Also, let's say we want to put a space station in orbit. One of the challenges with being in space is the fact that you are in a weightless condition. Why are you in a weightless condition as you orbit around space? So here's our rocket here, orbiting the Earth. There's gravity there. A lot of people say, oh, there's no gravity in space. No, if there's no gravity in space, then the moon would fly off and we would fly away from the sun. There's gravity everywhere. This equation never says gravity stops. So what keeps them going around is gravity. And so they feel gravity, even the astronauts in the space station. The gravity up there in the space station is only a little bit less than it is on the surface of the Earth. Because the surface of the Earth is several thousand miles in radius, and they're only 100 miles above that. So it's only 1 or 2% difference. The reason they feel weightless is because of this. While they're orbiting, they're actually falling. When you fall to the Earth, you don't feel the effects of gravity because you're accelerating. And the acceleration makes you feel like you're just moving, accelerating at the speed. So whatever you're with, when you jump out of your airplane, you and your buddy, you jump out, you fall, you accelerate together, you don't feel the effects of gravity. Okay? And so that's what happens here. The reason that astronauts are weightless is because they're continuously falling. If you ever gone to like Six Flags, and I think it's, oh, I can't remember what it's, Superman or whatever, where they take you up, you just ride in this thing and they take you up, and then they just drop you and let you fall. And when you fall, for that brief moment while you're falling, you feel weightless. You don't feel any effects of gravity. Your body starts and your hands start to float. If you put a penny there, then the penny starts to float right above you, okay? Because it's falling at the same speed that you are. In fact, that's how they train astronauts to get ready for this weightless condition. Is on Earth, they take them up into an airplane, they go as high as they can, like 50,000 feet, and then they just let it fall. They let it fall towards the Earth, and so while they're falling, everybody in the airplane has this weightless condition. And they can fall for about 30 seconds, and then they have to pull it out at the end and do the whole thing again. And so you only get about 30 seconds of weightlessness, and then when you pull at the bottom, you pull a whole bunch of G's, and most people get sick, so that's why they call it the vomit comet. It used to be a comet airplane, and so everybody would get sick and throw up because your body doesn't like that, the continuous changing of motion there. So astronauts are weightless because they're continuously falling around the Earth. It's not because there's no gravity. There is totally gravity up in space. Okay? Gravity from all objects up in space. All right. Another thing I want to show you. Still having to do with gravity. Well, all this has to do with gravity. Is we said that gravity here is equal to G m1 m2 over r squared, right? Well, let's say it's going to be the mass of the apple and the mass of the Earth. And this would be the radius of the Earth. So, for my apple that's going to fall in Newton's orchard, this is the mass of the apple times the mass of the Earth divided by the distance between it squared. Who's that squared? That's pretty good. Okay? But we know from Newton's second law that F equals ma. So I can plug that in for a force, because this is just a force, that's a force. So the mass of the apple times its acceleration is equal to g, the mass of the apple, mass of the Earth, over the radius squared. Radius of the Earth squared. Well, look, those cancel. So the acceleration of the apple, this is the mass of the Earth, over the radius of the Earth squared. What Newton realized, g is a constant, that's just a number. The mass of the Earth is just a number, so how many kilograms the Earth has. The radius of the Earth is a constant. These are all constant numbers. That's just a number. And so we usually write this as little g, and it equals about 9.81 meters per second squared. Or, if you like old-fashioned units, 32 feet per second squared. So on the surface of the Earth, the radius of the Earth, this is a constant, which means he proved what Galileo figured out experimentally. Galileo said, well, if they're the same size, they're going to accelerate the same. Newton said, yeah, because of my law of universal gravitation, the masses cancel. You and your friend jumping out of an airplane, even if your friend's a lot more massive than you, will still fall at the same rate, ignoring air friction. Now, air friction changes things, but without the effect of air friction, you would all fall, everybody would fall exactly the same rate on the Earth. All right, and when you go to other things, like when they went to the moon, the difference is this becomes the mass of the moon over the radius of the moon squared, and it's about 1/6 this value. So the guys walking on the moon felt about 1/6 the amount of gravity that they did on the Earth, which is really good because when they're wearing the spacesuits with all the packs and all the equipment as they were walking around to the moon, they were over 300 some pounds. It was hard for them to even function or even get up on Earth with all that equipment on. Where on the moon they were bouncing around having a good time because to them it felt like they only weighed about 50 pounds. So it worked out really well. I mean, it worked great on the moon because they had such big, bulky spacesuits and everything to move around on. All right. Let's say I wanted to put a space station up in orbit. One of the best ideas is to put a space station that is a cylinder here. The idea is, if you have somebody standing on the outside of a cylinder, and you spin the cylinder, so this is the axis in the center, and the whole thing is spinning. If it's spinning, then because of inertia, Newton's first law, you are trying to go in a straight line, but the walls are making you curve. If that's the case, then you're going to feel like there is a force to the outside, what they call a centrifugal force. It's actually not a true force. It's the same force as if you have your car and you make your car go around a corner. When you make your car go around the corner, here's the driver over here, somebody over here is going to feel a force that's going to make them feel like they get pushed to the outside of the corner. Or you take advantage of this. Back in the day when I was growing up, we had cars that had what they called bench seats, where there was one seat all the way across. You can put more people than 2 seats. Now everything has bucket seats. But you could put in here, and your girlfriend would come and sit over here, and you pick her up, and then immediately you can make a hard right turn, and she just feels all of a sudden this force, and she slides over right next to you. Taking advantage of physics. Same thing here, but we're going to take advantage of that to make what we call an artificial gravity. So as we're spinning around here, it feels like there's gravity there. Well, that's good because it's bad on our bodies to be in this weightless condition we were talking about, just floating around. Your bodies tend to atrophy. Your muscles do best when they work. And on the Earth, we're continuously working against gravity all day long. But that's good for our body. Well, when you don't have to do that, your muscles start to go away, your bones start to decalcify and get weak. And so astronauts actually have to spend several hours each day exercising on the space station to try to keep themselves in shape. Otherwise, when they come back to Earth, they can't even function. They have to rebuild up all their muscles. So let's say you wanted to make a space colony, a really, really big space colony, with like tens of thousands of people. Well, you make it this giant cylinder, and then on the outside of the cylinder, you build these buildings, like skyscrapers. But they're all pointing towards the center, and as the thing rotates, you're going to feel this pull to the outside, which would be pretty cool. Now, there's advantages and disadvantages to this. So you could have this thing, you could have things like lakes and rivers. It'd be really creepy because you'd be looking up and you could see a river above you, flowing just like normal. We're not used to this, being on the inside of a curve. We live on the Earth, we're on the outside of a curve. Okay? And gravity would vary, or this artificial gravity, it's not real, it's not actually gravity. But you would feel this effect, and as you got closer to the center, the effect would get smaller and smaller and smaller. And once you climb, so if you had a ladder all the way to the center, you get to the center, you would feel totally weightless. And then if you had the ladder coming down the other side, over here, then you would feel more and more